So now there's some vocab I wanted to mention. There's internal forces. So these are the forces that the particles of a system exert on each other. There are external forces. So these are the forces exerted on a system from outside the system. And there's something called an isolated system. So this is a system on which no net external forces act. So we're going to use these terms later. So we talked about momentum. So now the question is, when is the total momentum of a system conserved? Let's say that two blocks are colliding with each other. So we got block A and we have block B. And let's say that these blocks are in outer space. When the two blocks collide with each other, block A is going to exert a force on block B, and block B is going to exert an equal and opposite force on block A, right? Because of Newton's third law. So let me label that. Okay. So note that these are internal forces, right? These are the forces that the particles of the system exert on each other. So there's no external forces here since we're in outer space. Therefore, the system is isolated.
Approximately. I mean, there are some force in space.
Yeah. All the external forces are negligible, let's say that. What I can do is use Newton's second law in terms of momentum right here. Let's look at A and B separately. So for A, and this is going to equal dPA dt. Okay, so what's the net force acting on A?
FB.
Yeah, we just have FB on A. So this equals FB on A. And we can do the same thing for block B. So the sum of the forces on block B equals the derivative of PB with respect to time. So the only force on block B is FA on B. And remember from Newton's third law that these are action reaction pairs. That means that this equals negative FB on A, right? Okay, so what I can do is I can add these two forces. So FB on A plus FA on B. And what is that going to equal?
Wouldn't it be zero?
It'd be 0, yeah. Because remember, FA on B is negative FB on A. It's going to cancel out. The question we're trying to answer is when is the total momentum of the system conserved? So let's relate this to momentum. FB on A, that's dPA dt. And FA on B, that's dPB dt. And we know by the sum rule in calculus that the sum of the derivatives equals the derivative of a sum. So I can write this as the derivative of PA plus PB. So this is very interesting. We have the derivative of something is 0. So that means that something is constant. That means in this case, the total momentum of the system, which is PA plus PB, is conserved because PA plus PB is constant because its derivative is 0. So I'm going to write the total momentum of a system is conserved. So basically, P before equals P after if no net external force acts on the system. We only have internal forces here. We just have A applying a force on B and B applying a force on A. If there were an external force, if there was like friction on A, for example, then I would have a plus friction term here, right? And that would mean that the sum of the forces would not be 0. So this derivative here would not be 0. So the total momentum of the system would not be conserved because we have that external force on one of the blocks. So now that we know when the total momentum of the system's conserved, let's talk about the different kinds of collisions we're going to deal with. So there's elastic collisions. So an elastic collision is a Collision in which both the total momentum and the total kinetic energy of the system are conserved. An inelastic collision, still the total momentum of the system is conserved, but the total kinetic energy after the collision is less than before. So there was some loss of kinetic energy. There's completely inelastic collision. So it's a special kind of inelastic collision in which the colliding objects stick together and move as one object after the collision. Let's do an example. Classic ballistic pendulum example. A ballistic pendulum is a simple system used to measure the speed of projectiles. A bullet of mass mb strikes a block of wood of mass mw, suspended like a pendulum. After the impact, the block with the bullet embedded swings upward to a maximum height h. Determine the initial speed of the bullet. Okay, so let's draw a picture. All right, so this is the pendulum, and we have a bullet going towards it at some unknown initial speed, v1. And then the bullet hits the block and it gets embedded in the block. So that's going to look like this. So let's say that's the bullet. And now let's say that the block bullet system is moving at a speed v2. And lastly, it swings upward to a maximum height h. So that looks like this. So this is going to be y equals 0, and this will be h. I'm going to call this 1, and this will be 2, and this will be 3. So we want v1. So to find v1, we have to look at 1 to 2. Is momentum conserved from 1 to 2?
Yes.
Well, let's see. So momentum is conserved when there's no net external force acting on the system. So let's look at the forces on the system in 1 and 2. So we got gravity, MWG, and we have tension. These are external forces, right? The internal forces are the forces that the bullet and the block have with each other. But these external forces cancel out. So there's no net external force. So same thing with 2. We have tension and force of gravity, so they cancel out. So there's no net external force. So yes, momentum is conserved from 1 to 2. So I can say that the total momentum at 1, which is PB1 plus PW1, is going to equal the total momentum at 2. So PB2 plus PW2. So PB1, that's just MB V1. And initially the block is at rest. So PW1 is 0. And for 2, the block and the bullet are together. So the momentum for the bullet is MB V2, and the momentum for the wooden block is MW V2. So I can just factor out the V2 and write that as MB plus MW V2. Okay, so we're trying to find V1, so I'm gonna divide both sides by MB. So we have everything except V2, because we have all the masses. The problem says that the mass is MB and MW. So now we have to find V2, and to find that, we have to look at 2 to 3. So can I use conservation of momentum from 2 to 3 to find V2?
No,
And why not?
because tension does not equal gravity, I believe.
Yes, the net external force is not 0 because as the block swings, the force of gravity and the string tension don't cancel out when the strings are inclined. So since momentum's not conserved in this stage from 2 to 3, let's write an equation involving energy to find V2. So at 2, we have only kinetic energy here because we're at y equals 0, so there's no gravitational potential energy. So I'm gonna say K2 equals, and then over here, what's the velocity of the block bullet system when it's at its maximum height h?
0.
Yeah, so V3 equals 0 meters per second. All right. By the way, I'm defining x to the right as positive and y upward as positive. So there's no velocity, so there's no kinetic energy, but we do have gravitational potential energy because we're at a height h. So we do have UG3. What about the non-conservative forces? So I looked at gravity, that's a conservative force, but we also have tension, which is a non-conservative force. Should I include that in my energy equation? Should I include plus work done by tension?
Seems reasonable.
It seems reasonable, but appearances can be deceiving. So I don't have to take tension into account because it's perpendicular to the displacement. So it does no work. So we don't have to worry about that, even though it's a non-conservative force. So yeah, the work done by the non-conservative forces is 0. So we have that the total mechanical energy is conserved as the block swings, so from 2 to 3. The kinetic energy is not conserved because we lost some kinetic energy due to sound and deformation and all that stuff. So what kind of collision is this?
This is very inelastic.
Specifically, it's a completely inelastic collision because
When everything sticks together, the bullet is embedded in the block.
yeah. So K2 is 1/2 mv squared. So M is the total mass of the block bullet system. So it's MB plus MW. And we have V2 squared. And then UG3, it's MB plus MW times GH. The MB plus MW nicely cancels out. We can find V2. We just have to multiply both sides by 2 and take the square root. So V2 equals the square root of 2GH. So we have V2, so I can just plug that in here and we'll have our initial speed of the bullet. So it's just MB plus MW divided by MB times the square root of 2GH. Okay, so that's the magic of conservation of momentum.